Right now, as you're watching this, a radio signal from NASA's Voyager 1 spacecraft is somewhere in transit, crossing the empty dark between here and the edge of known space, and it will take almost a full day to arrive. Not an hour, not a few minutes, like a call to the International Space Station. Nearly 24 hours, one way. For a message traveling at the fastest possible speed anything in this universe can travel. And in just a few months, that delay is going to cross a threshold no human-made object has ever reached in the entire history of our species. This is the real story of just how far away Voyager 1 actually is right now, what the distance is doing to the way NASA communicates with it, and the exact moment, already locked into the calendar, when it becomes the first object humanity has ever built to sit a full light day from home. Every figure in this video comes directly from NASA's own tracking data and public statements. Not estimation, not exaggeration, just the genuinely staggering reality of where this nearly 50-year-old spacecraft actually is right now. Let's start with the number itself, because it's almost too large to process in any normal, everyday way. As of right now, Voyager 1 is a little over 15 billion miles from Earth. And according to NASA's own tracking data, a message sent from Mission Control currently takes somewhere around 23 hours and 50 minutes to actually reach the spacecraft. Think about what that means in practice. If an engineer at NASA's Jet Propulsion Laboratory in Pasadena sends a command up to Voyager 1 first thing in the morning, that signal is still traveling through space that entire day, arriving sometime the following morning, nearly a full rotation of the Earth later. And that's just the outbound leg. Any response Voyager 1 sends back takes almost the exact same amount of time to return, meaning a single, complete exchange, a question and an answer, currently takes very close to 2 full days from start to finish. This isn't a new problem for the mission, but it is one that has been quietly getting worse every single year since the spacecraft launched, and it's about to reach a genuinely historic tipping point. Voyager 1 launched on September 5th, 1977 from what was then Cape Kennedy in Florida, at a time when Jimmy Carter was president. Personal computers barely existed outside of hobbyist garages, and Star Wars had been in theaters for only a few months. Its original mission was designed to last around 5 years, just enough time to fly past Jupiter and Saturn, take some photographs, and quietly conclude. It reached Jupiter in March of 1979, discovering active volcanoes on the moon Io along the way, and it reached Saturn in November of 1980, capturing detailed images of the planet's rings and its massive, hazy moon Titan. Voyager 1 has been moving in essentially a straight line since that Saturn flyby, when it used the planet's gravity for its final trajectory adjustment, and then simply kept coasting outward at roughly 38,000 miles an hour, a speed it hasn't needed to change since. Every single year, that constant velocity adds about 3.5 astronomical units of distance between the spacecraft and Earth, with 1 astronomical unit being the entire distance separating our planet from the Sun, 93 million miles. So every year, Voyager 1 puts more than 300 million additional miles between itself and home, permanently, with absolutely no way to slow that separation down. According to NASA's own calculations, that steady, unstoppable drift is going to carry Voyager 1 across an actual historic threshold on November 18th, 2026, at exactly 16 minutes and 7 seconds, past 2 in the morning, Pacific time. At that precise moment, Voyager 1 will be 16,094,799,096 miles from Earth, a distance so specific that NASA has calculated it down to the mile because at that exact distance, light itself, moving at its universal, unbreakable speed limit, takes precisely 24 hours to cross the gap. Voyager 1 will become the very first human-made object in the entire history of our species to reach that distance, a full light day from home. While it is still alive, still transmitting, still doing real science from a place nothing we've ever built has gone before, Susie Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, has described exactly what that milestone is going to mean for the day-to-day reality of running this mission, and her explanation makes the abstraction of light speed delay suddenly feel very concrete. She's explained it this way. If she sends a command and says good morning to Voyager 1 at 8 in the morning on a Monday, she won't actually receive Voyager 1's response back until roughly 8 in the morning on Wednesday. Not because the spacecraft is slow to respond, but because the message itself needs a full day just to reach the spacecraft, and then another full day for any reply to make the return trip home. Every single interaction with this machine, from this point forward, effectively becomes a 2-day conversation, regardless of how simple or urgent the message actually is. This gets genuinely serious when you consider how the Voyager team is currently trying to manage the spacecraft's rapidly diminishing power supply. Voyager 1 runs on 3 radioisotope thermoelectric generators, devices that convert heat from decaying plutonium into electricity, and that output has been steadily shrinking for nearly 5 decades, as the plutonium inside them gradually decays, losing a small, fixed percentage of its usable energy every single year, regardless of anything engineers do to manage it. This year, in an effort to squeeze more usable power out of an aging, imperfect electrical system, NASA engineers have been testing an experimental procedure, informally nicknamed the Big Bang, designed to restructure how power flows across the spacecraft in hopes of recovering small pockets of unused capacity trapped inside its aging components. Capacity that may exist simply because certain parts of the spacecraft's electrical system have grown less efficient with age than they were when Voyager 1 first launched. That procedure was tested first on Voyager 2 back in May of this year, specifically because Voyager 2 has slightly more power to spare and a shorter communication delay, making any potential failure somewhat less catastrophic to the overall mission. If those tests succeeded, the plan called for engineers to attempt the same fix on Voyager 1 itself no earlier than July, which is happening right around the time I'm telling you this story. And here's the part that should genuinely give you a sense of just how high the stakes are. This isn't a small, low-risk software patch. It's a full rewiring of the spacecraft's power hierarchy, executed entirely through remote code sent across billions of miles of empty space. If something goes wrong during that transition, if a critical heater fails at the wrong moment, the fuel lines feeding Voyager 1's small maneuvering thrusters could freeze solid. And if those thrusters freeze, the spacecraft would lose its ability to keep its antenna precisely pointed back toward Earth, which would effectively end the mission permanently, turning Voyager 1 into a silent, multi-billion-mile-long piece of drifting metal, still out there, but never able to speak to us again. Every single step of that procedure has to be conducted with the same brutal, unforgiving delay hanging over every decision. Send a diagnostic command, and it takes nearly a full day just to arrive. Wait for a response confirming whether it worked, and that takes another full day to come home. There is no way to watch this unfold in real time, no way to catch a mistake as it happens and immediately correct it. Every single choice made about Voyager 1's future right now is being made blind, based on data that's already the better part of 2 days old by the time anyone on Earth actually gets to see it. There's also a technical side to this story that doesn't get talked about nearly enough, because distance isn't the only problem Voyager 1's signal has to overcome. As the spacecraft gets farther away, its signal doesn't just take longer to arrive, it also gets dramatically weaker, spreading out across an ever larger area of space the same way a flashlight beam fades the farther it travels from its source. By the time Voyager 1's transmission actually reaches Earth, it's astonishingly faint, a whisper of radio energy that has to be captured using NASA's Deep Space Network, a system of massive dish antennas, some measuring 70 meters across, positioned in California, Spain, and Australia specifically, so that at least one of them is always pointed toward the spacecraft as the Earth rotates underneath it. Even with those enormous dishes, and even combining the signal from multiple antennas working together at once, Voyager 1 currently transmits its scientific data back to Earth at a rate of only about 160 bits per second, a speed so slow it's genuinely comparable to an old dial-up internet connection from the 1990s, the kind that used to take minutes just to load a single low-resolution photograph. Susie Dodd has explained that gathering even this modest, extremely sparse trickle of information requires the full cooperation of multiple antenna arrays working in concert, and that the low data rate means her team often receives only limited insight into the spacecraft's actual health at any given moment, making it that much harder to react quickly if something does go wrong. To really appreciate how strange this situation is, it helps to compare it to communication delays humanity has dealt with at every other stage of space exploration. When Apollo astronauts stood on the lunar surface and talked with mission control back on Earth, there was a delay of about 2.5 seconds round trip, just barely long enough to notice if you were listening closely to old recordings, but nothing that meaningfully disrupted a conversation. Sending a signal to Mars, depending on where the two planets sit in their orbits, takes anywhere from about 4 to 24 minutes one way. Annoying for real-time control, but manageable for a robotic rover with enough onboard intelligence to make its own short-term decisions. Reach all the way out to Jupiter, and that one-way delay stretches to nearly 52 minutes. Even Pluto, sitting way out at the edge of what most people think of as our solar system, only requires about 6.5 hours for a signal to arrive. Voyager 1 blows every single one of those numbers away. It is so far outside the range of anything else humanity has ever operated that the normal rules of mission control, quick diagnostics, rapid troubleshooting, immediate course correction simply don't apply anymore. Every problem with Voyager 1 becomes what engineers have started calling a 2-day conversation, a pace of communication that forces an almost meditative patience onto a team working with equipment that is, by any modern standard, extraordinarily old and extraordinarily fragile. This isn't a hypothetical concern either. It's already happened, and it happened at the worst possible moment. Back in November of 2023, Voyager 1 began transmitting garbled, unreadable data, the result of a single degraded memory chip inside its flight data system, the component responsible for formatting scientific data before it gets sent home. At the time, the one-way communication delay was already running at about 23 hours, meaning every single attempt to diagnose the problem, form a theory, test a fix, and see whether it worked required the better part of 2 full days to complete a single cycle. It took NASA's engineering team roughly 5 months of that agonizingly slow process, patiently working through the problem one careful, methodical step at a time, essentially performing remote surgery on a computer system built in the 1970s using nothing but patience and a communication link slower than dial-up internet, before Voyager 1 finally resumed sending clean, readable data again in April of 2024. That entire ordeal played out at a communication delay slightly shorter than what the spacecraft is experiencing right now, which gives you a real sense of just how much harder every future problem is going to be to solve as that delay keeps climbing toward and eventually past the full 24-hour mark. And here's a detail that puts this entire milestone into perspective in a way that I think genuinely deserves a moment of reflection. Voyager 1's twin, Voyager 2, launched just 16 days apart from its sibling back in 1977, took a longer, more roundabout path through the solar system, flying past Uranus and Neptune along the way, rather than heading directly out toward interstellar space the way Voyager 1 eventually would. Because of that different trajectory, Voyager 2's is currently sitting at a communication delay of only about 19.5 light hours, meaningfully closer to Earth than its twin, and it isn't expected to cross its own 1 light day threshold until November of 2035, nearly a full decade after Voyager 1 does. 2 spacecraft, launched within 16 days of each other, from the same launch pad, carrying nearly identical instruments, sharing nearly identical hardware, and yet the paths they've traveled since have quietly pulled them apart into 2 very different journeys through the dark, on 2 very different timelines toward the exact same kind of historic, humbling distance. It's a reminder that even something as fixed and deliberate as a spacecraft's trajectory can lead 2 nearly identical machines toward wildly different futures, simply based on a handful of early decisions made by mission planners working almost 50 years ago. So here's what I actually want you to sit with. Because I think it's easy to hear a number like 1 light day and let it wash over you as just another impressive sounding space fact. Try to actually hold it in your head for a second. Every single message currently traveling between Earth and Voyager 1 spends nearly an entire day in transit, alone, in the silent dark, covering more than 16 billion miles before it ever reaches its destination. A machine built in the 1970s, using less computing power than a modern digital watch, is still out there right now, still listening for those messages, still occasionally sending its own data back across that same vast gap, patiently, reliably, the way it has for nearly 50 consecutive years. In just a few months, on a specific morning already marked on NASA's calendar down to the second, that gap is going to officially become the single largest distance any human-made object has ever operated across, while still remaining in active, functioning contact with the people who built it. There's something worth appreciating in just how deliberately unglamorous this entire achievement actually is. Nobody designed Voyager 1 to still be running in 2026. Nobody designed it to become the first object in human history to reach a full light day from home. It was simply built well by engineers working with slide rules and hand-drawn schematics, tested rigorously and then quietly, patiently maintained by generation after generation of mission controllers who inherited a spacecraft older than most of their own careers. That combination, careful engineering from nearly 50 years ago and equally careful stewardship ever since, is the entire reason this milestone is even possible. There was no guarantee Voyager 1 would still be functioning by the time it reached this distance. It simply kept working, year after year, far longer than anyone in 1977 had any real reason to expect. If you want to be here for the moment Voyager 1 actually crosses that light day threshold, subscribe and turn on notifications, because November 18th is coming fast, and we'll be covering it in real time when it happens. Drop a comment telling me what you think the very last message NASA sends to Voyager 1 should actually say. Because whatever it ends up being, it's going to spend nearly 24 hours in complete silence before this incredible, aging little spacecraft ever gets the chance to hear it.